then see then the advantage that you automatically see is the following. So it looks like right, if I had a stack and if no pixel moves, let me go to another slide and let me move down. So what this means is, right, if you capture, okay, a number of frames like that, right, which is what is called a stack. Assume that you capture 30-40 frames like that, right. So it's like saying that I have a Z stage, I kind of keep on, right, moving it up, and I capture a bunch of frames. Now the nice thing, right, that you saw is that because of a telecentric setup, if I look at a point here, the same point exists exactly at the same place in my next frame. The same point exists exactly at the same place in the last frame, right. Nowhere has it moved. The degree of blurring around it is, of course, is changing, right, because of the fact that I am kind of moving this stage. So therefore, in some frames, right, this point is coming in focus maybe here, and then afterwards it's getting blurred maybe, or maybe some other point is coming in focus in the first frame, but then it becomes blurred later. Okay, we don't know, something like that is going on. But what this also shows is that here is a cue for depth, because if by some means, right, if now again, right, let's go back to this kind of fictitious focus operator which we think we have with us. If we had that operator and and let's say if we could apply it here around this pixel or on that pixel, typically it's around, okay, in and around that pixel, or let's say I just apply it on the pixel, and then if I compare, let's say that this focus measure operator says, outputs a value, says that, okay, right, this is the degree of sharpness. Now by just by looking at that, it doesn't, right, it's not even clear, I mean, right, what do I tell about that? What is that absolute number? What does it mean? But now if I go to the next frame, I ask the same operator around the same point, I ask what is the degree of sharpness. Now it says, let's say earlier it said 40, now it says 30. Then I know that, right, it's getting blurred because my sharpness is kind of reducing. And then maybe, right, sometimes later it probably increases, I do not know, and then somewhere in between, right, maybe in some place it says that it's 80. Okay, so relatively now I know, okay, because the underlying image is the same, no, nothing has moved, there's no image motion. All that is happening is that my say level of blur is changing, and therefore relative to the other frames, you can talk about some frame where this point is coming into focus, and the same holds good for every point, right. So the nice thing about this is that as long as you can ensure that every point in the 3D object comes into focus in one frame or in some frame or the other, you are fine. Then that by itself that's why it's called shape from focus. It doesn't say shape from defocus. Shape from focus, because you have to look for the point, look for the frame in which a point is appearing in focus, and each point can come in focus in whatever frame it wants, right, depending upon the nature of the underlying object. Okay, so that is why it's called shape from focus. And why you wanted to talk about this is because now that you understand, let's say if I showed you one of these images, you know exactly what is going on, right, how this lens is introducing that blur. But now we are going one step forward and utilizing whatever we've learned in order to be able to solve something like an inverse problem. Now we are asking for a 3D scene given this bunch of frames. Okay, any doubt at this point before I go further? Okay. Now I'll just draw this setup, okay, and these are all real images, okay, captured in the lab. Okay, don't think that right, I just synthesize them or something. These are real, okay. All right, so the way it looks like is the following. Okay, I'm just going to draw this small little diagram. So the SFF setup, right, looks somewhat like this. So you have your image plane here, and no, of course you could have also drawn it from left to right, but I'm drawing it top bottom because typically it's like a Z stage, and then you move along the optical axis. So I'm drawing it top down. So this is the image plane, let's say, and then somewhere here is your lens. Okay, so let's call this as some U. Should I draw it in some blue or something? Okay. So this is U. So the image plane to lens distance is U, and let's say that that you have the plane of focus, right, is somewhere here. The plane of focus means that for that focal length of this lens, whatever it is, right, some f, right. So where this lens law is getting satisfied, so your omega d, right. So omega d is calculated from the lens center. So this is your omega d, which is a working distance, right, which we actually talked about. That means any point that is kept here will appear in focus, correct? That's what we mean when we say it's a working distance. Plane of focus means a point that if you keep an object here, exactly anywhere on this line, it will come in focus because it's exactly satisfying Lenz's law. And then down below we have actually a 3D object. Let's say right here is our 3D object, some shape, okay, some shape I have, and whose shape I want to actually find out, right? I want to find out what kind of 3D surface am I kind of right looking at. And this 3D surface, right, what you do, okay, let's call this as the Z stage. Okay, this is called the Z stage, and then this is called a reference plane. Okay, so here is where we start with. Okay, so we start from here. Okay, so we start from here, and then right, what we do is so for example, right, so with respect to this plane, okay, reference plane, we'll take one image, okay, with this setup. Then what we do is we actually move the stage up by an amount, let's call that delta d, okay, up by delta d. Now delta d is something that we will talk about later. Just assume that it's a kind of translation along the z axis, okay. So here is your optical axis of the camera is this, okay. If I show like that, you don't see, right? So okay, so here is your optical axis, right? So you're moving it along that, right? Now assume that I actually move the stage up right there. Okay, so from here to here is really a translation of delta d. Now how to choose this delta d and all that we'll talk about later. Let's say that I just shift it up by delta d. Therefore, what will happen? So this guy will now kind of say come up, right? And then okay, I'm kind of roughly drawing it. Okay, so then you're there. Okay, and then you again move it by another delta d, like that you keep doing. Let's say that you're somewhere here. Okay, you could say traverse several delta d's, and somewhere okay, no, not there. Let's see. I wanted to. Okay, now let us say that right, we are somewhere here. Okay, and then from here, okay, all right. I mean, assume. Okay, what I want to show is, okay, maybe I should go a little lower. Okay, so let's say I'm here, and suppose from here I draw. I want to show something like that. Okay, it's not exact, but then I just want you to understand that, right, there will come a point, right, when this guy, which is the peak of this surface, right, will actually hit that plane. Okay, will hit your plane of focus, which means that all through, right, if you're watching this point, okay, all through, I mean, in the beginning it would have been blurred because it is farther off from your plane of focus. You kind of brought it up a little closer, it would have become a little more focused, and then you keep doing it. Maybe it came much more into focus, but right now at this point it's perfectly in focus, correct? And then of course, and then you go on, right? I mean, you don't stop there. Then maybe at some other point, right, you draw again, and then this object kind of goes like that, right, and so on. Okay, so the idea is to be able to sweep through the whole object, right? Take a bunch of frames so that right, you can actually sweep through the whole object. So the idea is this. Okay, so for example, at some frame, okay, so because you move delta d, let's say you move by whatever m number of frames. Let's say at the mth frame, right? So as far as the point here is concerned, right, this came into focus in the mth point, and after that, right, it became blurred because of the fact that you are now out of the focal plane, right? So it'll be like gradually coming into focus, then it hits the plane, it's perfectly in focus, then again it becomes blurred. Now imagine some other point here, right? So for example, this guy, right, it doesn't come into focus in the same frame, right, as this, because this came into focus in kind of a different frame. This would have come into focus in some other frame, right, after you lifted it some more. So the whole idea is that in that stack then, so if you now imagine the stack, right, which is like the frame that you capture for every one of these the delta d's. So imagine the lowermost is when you are at this reference plane. Then you see up delta d, maybe right, this one, and then there are several more, right, a lot more that you have captured, and then you have a whole stack now. So now what we are saying is, as long as every point in this 3D object, okay, at least appears in focus, in some frame or the other, okay, then you know the Q for depth, because then see, then the point is this, right? If you know how do you really think about estimating depth? Let me say that for this point, right, I'm going to indicate something, right? I'm going to say that this quantity, I'm going to call this as d bar, okay, similar to a disparity that we had there, right? I'm here going to call a quantity d bar. Now what is d bar? Okay, wait a minute. No, d bar is which way? D bar is the other way around. Yeah, not this. Ah. I have to be a little careful, okay, when I say that. Now, okay, now d bar is from here to here. Okay, so at the time when you start, right, when you start at a reference plane, okay, which is here, right, which is here is where we start. So from there, how much should you move, right? So here what this means is, so d bar is the quantity that basically represents by how much this state should be moved, right, in order for this point to appear in focus. Okay, let me write that down. Okay, okay, d bar represents, because the rest of the quantities you know what they mean. Okay, so d bar represents the distance by which the stage should be moved to bring a point into focus. Should be moved from its reference position. Okay, so it means that, right, I mean, there is a d bar for every point, correct? D bar is not really a global value. So for this point, this is the d bar. Let's say for some other point, right? So for example, for this guy, right, which is lying here, okay, so that is where we started. No, here is a reference plane, right? I think this got wiped out. Okay, here is our reference plane. So for this point, right, so d bar is going to be all the way from here to here, right? And if, for example, right, if I knew from where I was starting, see, d bar itself will give you the surface profile, right? If you simply plot d bar, you know that something is more, something is less, therefore you get a profile. If you want the exact height, then you should know this. No, let me call this as d ref, right? D ref, let's say, is something, right, which I know, okay, because right, I'm going to know from where I start. So if I know d ref, if I simply do d ref minus d bar, and if you're interested in this as the height, if you want to call this as the height, then all that you have to do is for every point, you simply have to say subtract d bar from actually d ref to get the height of the object. It doesn't matter. You look at you compute height or you simply compute d bar, both are equivalent, because d bar itself will give you how the surface is undulating, right? So the whole thing now boils down to, so what this means is that if by some means, if you can compute d bar at every this one, okay, location, if you can compute d bar at every this one location, so it's like saying that you have a d bar for this, you have a d bar for this. So d bar is like a function of x comma y, right? It will change all over the image, and therefore the output, right, of this whole thing should be something like another grid, which will be of the same spatial resolution as your image. Okay, it should have the same spatial resolution as your image, and on this, right, all that you would do is plot your d bar. So it will mean that, right, some will be high, some will be low, whatever, right? Some may be very high, whatever it is, right? So all these spikes, right, that you're plotting. So these spikes are your d bar, and they in turn tell you what is the surface now, right? This is okay. So which means that right, if let's say, right, somebody had actually de-blurred this image. Right? De-blurring means removing the blur. It's somebody had said that, you know what, oh, this is all blurred, right? And first of all, you can't use parallax idea, because nothing is moving, right? So in this case, even if you de-blur, you will get nothing, right? Don't go for actually de-blurring. Utilize whatever the lens is telling you in order to be able to recover some other information, right? So I think so that's why I said right at the beginning, new sense, or you see, right, new sense. So this is where blur makes new sense, right? So now the point is, now we will ask, how do we actually do this now, right? I mean, what will be that operator? Okay, what should we do in order to be able to get a sense for this sense for the degree of sharpness and all that? So all that banks upon something called a plot that is called a focus. Okay, let me write this as FM of D, and this, let's say, is D, and FM stands for focus measure. Focus measure, right? So it is some operator, okay, which we will also say derive. So this operator is something that when you kind of keep it at a pixel, it will give you some sense for sharpness. So now this plot, right? You will so this plot exists for each pixel. Okay, so it's not like a plot for the entire. No, it's not a plot for the entire image. Every pixel you will have this plot, and what this plot will tell you is, what this D simply means is, let us say that at D naught, which is where you are starting, which is a reference. At D naught, if you apply, and again, right, this plot exists for each pixel. So this plot is for a pixel, okay, or is it it is being evaluated for a pixel, or you want to say at a pixel, whatever, right? So this plot is being evaluated at a pixel using maybe, right, some small sort of a neighborhood maybe, right, or it could be simply that pixel itself. So at a pixel, you are looking at in a frame, right? So you can imagine that you have all these frames. So you are kind of so you are standing somewhere here in one frame, and right at a pixel, and you are asking, applying this focus operator and asking what is the value, right? And suppose, let's say, right, it tells you that the value, okay, so the sharpness is somewhat like this. Then we ask in the next frame, up, right, go up, and then look for, at the same location, look for the sharpness again. And suppose, right, in this case, it turns out that let's say that it turns out that D1, which is the next frame, that means these two are separated by actually a delta D, correct, because you have this delta D apart, and we kind of keep delta D uniform, because we don't want to make the math complicated. Actually, it's a very simple technique, okay, so that's its strength. So D1 is this. So let's say that D1 shows up there, and then again, right, let's say D2, okay, is something else, something else, and then we go on, okay, like this. And let's say at some place, let me call that DM minus 1. Okay, let me say that I observe something like that. And what is special about this DM minus 1 is that at DM, right, I find something like that, let's say, and at DM plus 1, let me say that I find something like this. Now, do you think it's okay to plot it that way? See, this is delta D, so is this. But I have said that the focus measure may give something higher on the left and then lower on the right, or maybe lower on the left and higher on the right. Do you think I am drawing something wrong, or you believe that is okay? Should they be symmetric, or you feel that it's okay? One will be high and one will be low. Huh? You are kind of delta D away, exactly.
Cannot say that at DM it is actually focusing that point.
Correct. True. That is true. But I am saying, irrespective of whether DM is actually the place where the frame comes into the point comes into focus, but I am saying when you are delta D away from DM and delta D on the lower side and delta D the upper side, I am saying that your focus operator seems to sense that on one side it's higher and on one side it's lower. So I am asking, right, so should I have drawn it like this, or should I have drawn it like this, so that these two are exactly the same about DM, or should I not? Oh, is it like it will be wrong to draw them symmetric?
Could be symmetric.
Okay, what do you base that on?
At the
Mm-hmm.
maybe in between the delta D
Mm-hmm.
could be actually focus point.
Okay. Yeah, but I'm looking for something more concrete than that. Think. See, the way, right, I would argue is this. I mean, if you go back to the blur radius equation, right, what was it? Then we had a blur radius equation. RB was some R naught, U naught, 1 by omega D minus C 1 by D. Right. Now, the point is, right, so suppose let's say, right, suppose you have RB1, okay, which you got by being let's say 1 by D plus delta D, right, and then you got an RB2 which is like R naught U naught 1 by omega D minus 1 by D minus delta D, right. So you can see that right, if your frame is actually in focus, right, then there's no reason to believe that your blur radius has to be symmetric, or the blur radius should be the same on, right, either side of the kind of point of focus, right. So about, let's say, D plus delta D, and then another case it is D minus delta D, right. So it is not true that right, if you are sitting here and then this is the plane of focus, it doesn't mean that if I'm delta D away from here, then I will and if I'm delta D at the back, right, it doesn't mean that these two will actually introduce the same degree of blur. So let us say that if we assume that at DM, right, it comes into focus, then the simplest thing to do would be to have this focus operator run, right, on every frame at that pixel location or around that pixel, located at that pixel, and then it could sense around a small neighborhood, and then, right, and then it shows up this value, shows up this value, shows up this value, and then what you have. Let us say that, right, we assume that whatever we see here to be the highest focus measure value, and therefore one thing to do would have been to simply say that that point comes into focus at this frame, and therefore, right, therefore this should be my D bar. Okay, that need not be, because it could be that, right, we just kind of see overshot, right, because our delta D could have been such that we have quantized it in a manner that we could have just overshot, and we may still not be sensing exactly where that actually D bar is, right. Is it not? Because in this figure, see in this figure, right. So when you're moving by delta D, right, I mean, it doesn't mean that peak would exactly come and sit at the plane of focus. You could have just translated a little above, because you do not know, you do not know a priori what this 3D surface is. You are just moving randomly at delta D, and then you are hoping that everything will come into focus. But you could have just skipped the point of focus, right, because that is your actual D bar, and what this kind of an FM plot is giving is a sense of somewhere there. He tries to get this D bar through what's called a Gaussian interpolation. Through a Gaussian interpolation. Okay. And the way, right, this is interpreted is that, see, for example, if you try to fit a Gaussian, and the way he fits a Gaussian is, right, he takes these 3 points, right. So he takes a maximum guy. Okay, seemingly what is the maximum, and then around it you have the one on the left and then the one on the right. It could be that this is lower and that is higher, we do not know. But then he fits a Gaussian. So in this case, right, what would happen is, if you try to fit a Gaussian, okay, let me draw it with another color. So what it will do is, it will try to fit something like that. So this peak will be kind of to the left of DM. If it was the other way, then it would have been to the right of DM, right, if the right was higher. So he will try to find out hypothetically where this D bar is. And he uses the Gaussian interpolation, because if you use linear and all, you can never get a value higher than let's say, right, either of these two peaks, either of these two values. So this Gaussian interpolation allows you to actually pick somewhat like actually a peak now. Now there is no great theoretical support and all for this. He just does something very simple, because he wants everything close form and fast. And he uses Gaussian interpolation, because then that way, right, even if there is a peak somewhere to the left or the right, he will try to fit through that and be able to solve for D bar. And this is, and wherever he so the way he solves for is that, so let's say that if you call this as this value, let me call this as FM minus 1. Let me call this, where is that? Okay, so this value is FM. And let me call this value as actually FM plus 1, right. So the one that is a DM plus 1. Okay, that, let's say, that is the focus measure output. Then in this Gaussian interpolation, so he has actually 3 equations, right. FM on the one hand. So, he says is Fp, something that is not known, because he is trying to do a Gaussian fitting, e raised to minus of, let us say, dm minus d bar square by 2 sigma square. And he does not assume that this should integrate to 1 and all. So, this Fp need not be 1 by root 2 pi sigma and all. So, he allows it to be free. So, really the area will be like 1 by root 2 pi sigma times Fp. Okay. So, Fp is independent of sigma, some peak that you get there. So, it is not a Gaussian that is constrained to have an area 1. And then Fm minus 1 will be of course Fp e raised to minus of dm minus 1 minus d bar the whole square by 2 sigma square, and then Fm plus 1 similarly is Fp e raised to minus of dm plus 1 minus d bar the whole square by 2 sigma square. Okay. And so, since now you can take logarithm and all, right. So, the idea is that you can solve for actually d bar. Okay. So, the actual d bar, right, which you have here. So, using these 3 equations, he solves for d bar, and not only that, okay, he does not stop at solving just for d bar. He also finds out Fp, he also finds out sigma. Okay, I'll tell you what those things actually mean. I mean, why those things are relevant, might be relevant, right? So, and then once you find this d bar, and that is the d bar that will take for that pixel. The nice thing is that you can do all of this completely in parallel. You don't have to wait for one pixel output to start the next one, right? You can, if you have a parallel architecture, you can run all these plots, right, simultaneously, get d bar for every pixel, and then you can actually plot the surface. So, again, just as stereo has issues, right, this also there are some issues and all which I will talk about later.